In Chapter 4, Notes A, we will discuss the intricate details of both ionic and covalent bonding. Let's first discuss why two elements might bond. A bond is simply an attraction between two atoms or ions. And this is going to occur because it will lower the energy of the system, because it makes the compounds more stable. There are three main types of intramolecular bonds. Intra meaning between two atoms, or ions, I should say, either way. So we've got ionic compounds, which are typically between a metal and a nonmetal, covalent compounds between two or more nonmetals, and metallic compounds where metals are the only things involved. The metallic bond typically is more of a sea of metals, and the electrons are freely flowing like the electron sea model. So we're going to focus on the difference between ionic and covalent attractions today. There's a reason that we call that a rule of thumb as opposed to like the rule. That is not the law that every bond between a metal and a nonmetal would have to be ionic. There's a reason why these compounds typically fall into these categories. The categories are all based around a concept called electronegativity. First, to define electronegativity, it is how good an atom is at attracting bonding electrons. The electrons have to be in a bonded orbital. So this is why things like noble gases, we say, do not experience or have a measurable electronegativity because they don't have bonding electrons. Only compounds that want to form bonds in order to become more stable will enter these bonds and then have the bonding pairs of electrons. So if a compound is good at kind of hoarding that shared pair of electrons during the bond, then we would say it has a high electronegativity. Something that's not very good at attracting those bonding electrons would have a low electronegativity. We can actually quantify this thanks to someone named Linus Pauling. The Pauling scale goes as high as 4 all the way up in the corner by fluorine, and it goes as low as 0.7 on the opposite corner down by francium. Notice that the noble gases are not part of the Pauling scale since they don't enter bonds and therefore would not have a quantifiable bonding energy. So an atom that has a very great electronegativity or high electronegativity would be good at attracting those electrons. Whatever is attracting electrons would become the more negative side of the molecule. This is where polarity comes in. That side of the molecule would now have a partial negative charge. By default, the atoms then that have the lower electronegativity, or the part of the molecule where that electronegativity is less, would be deficit in electrons. And so we actually would call that more of the electropositive side of the molecule. Carbon monoxide is a great example. Oxygen is more electronegative than carbon, so the oxygen side of carbon monoxide would be partially negative, and the carbon side would be partially positive. Let's look at how electronegativity plays a role in the classifications of intramolecular bonds. If we look at an ionic bond, that's going to be between a cation and an anion, something with a low electronegativity and a high electronegativity. Low electronegativities would be on the left side of the periodic table, our metals. High electronegativities would be on the right side of the periodic table, our nonmetals. So typically speaking, a metal and a nonmetal would form an ionic bond. Polar covalent bonds are going to have dissimilar electronegativities. Not complete opposites, not a high and low, but something that's different enough to create a polar bond. Another type of covalent bond could be nonpolar, and then we would have similar or the same electronegativities, such as between a diatomic compound. These last two types of bonds would have small to negligible differences in electronegativities. So this is going to happen when you're bonding two or more nonmetals together. Because the nonmetals are up in the top right of the periodic table, they would typically have very high electronegativities, so the difference between them wouldn't be very great. I want to talk about one more main idea behind bonding before we move on to the specifics. Atoms want to be like their noble gas counterparts. The noble gases have completely full s and p orbitals. Since you can only have 2 electrons in s and 6 electrons in p, a completely full set would have a total of 8 valence electrons. This is known as the octet rule. All atoms will gain, lose, or share, do whatever it takes until they get 8 valence electrons. There's actually something called the duet rule as well, which is exactly what it sounds like. Very similar to the octet rule, saying we want to get 8 valence electrons, but the duet rule would refer to atoms that want 2 valence electrons. This would include hydrogen with an electron configuration of 1s1, which would like to gain 1 more electron to become a complete 1s2, and also lithium, whose electron configuration is 1s2, 2s1. It would want to lose 1 electron so that it can get to the complete configuration of 1s2. So both of these ions would like to be like helium, so that we would call that the duet rule, having 2 valence electrons. Let's get into ionic bonding in a bit more detail. Using the Pauling scale, we can assign electronegativity numbers to every atom, and then if we compare two atoms that bond, we can find what's known as the difference in electronegativity, or the change in those values. Typically speaking, a change in electronegativity that's great would be an ionic bond. But where exactly is that cutoff? I've typically said that an electronegativity difference of greater than 2 would be an ionic bond. That's in what a lot of the college textbooks around the country. According to IB, the electronegativity difference is exactly 1.8. So you're going to have to be a little bit flexible depending on the intent and purpose of why you need the difference in electronegativity. For your IB test, you need to go by an electronegativity difference of 1.8 and above would be considered an ionic bond. It may seem a little strange that a number like that is not so concrete, that can be subjective. And that's because what we're doing right now is really an oversimplification of this process. To say an atom is 100% ionic or 100% covalent, painting it as that black and white system is a complete mischaracterization of what's really going on. Instead, a better way to phrase that would be to say it has an ionic character or covalent character. It's really more of a sliding scale, a gray scale, where something that has absolutely 0 electronegativity difference would be covalent, something like a diatomic hydrogen. The largest electronegativity difference would be the most ionic compound. So, for example, if francium could bond with fluorine, that would be the most ionic compound. And everything in between is just a variation of that ionic and covalent character. The closer to ionic we are, the more polar that compound gets. Where exactly it crosses to being called covalent or called ionic in the simplified version of things, according to IB, that's when the electronegativity difference is greater than 1.8. To simplify that a bit, basically the greater the difference in electronegativity, the more ionic the bond. If it is a difference of less than 1.8, we would say the more polar the bond. So if we apply this idea that we want a great difference in electronegativity to be an ionic bond, we are going to be looking at the metals that are on the left side of the periodic table and the non-metals that are on the right side of the periodic table. But we're going to specifically narrow this down to groups 5, 6, and 7, not anything in group 4. We will discuss group 4 in notes E when we talk about the network covalent bonding that occurs. But for right now, we're going to focus on ionic bonding between metals and groups 5, 6, and 7. Let's break down a very common ionic compound, sodium chloride, or table salt. If you look at the element just the sodium, the regular sodium atom would have the electron configuration 1s2, 2s2, 2p6, 3s1. That last orbital would be its valence shell, principal quantum number of 3 being the highest. So that means it only has 1 valence electron. So in order to meet the octet rule, or to become like neon, it would want to lose that 1 electron. That would give it a complete outer shell now in the second energy level, 2s2 and 2p6. Now let's look at just the chlorine atom. with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5 as the atom, the valence shell here would be the 3s2 and the 3p5 for a total of 7 valence electrons. So it would want to gain one more electron to have a complete outer shell in the third energy level, 3s2 and 3p6, to make it like argon. So having chlorine gain the one electron that sodium lost is going to make both atoms have a complete octet. It will also leave sodium with a positive charge and chlorine with a negative charge. The positive and negative will attract, and there's a special name for that. We call them electrostatic attractions. This is not a physical bond, but a static attraction in between the positive charge and the negative charge that will pull the two ions together. Now this next part may be new. Although one sodium atom attracts one chlorine atom, those ions do not exist in isolation. That is simply the ratio of how many sodiums to how many chlorines exist in the lattice structure of the ionic compound. So if we look at a 2D slice of this, we can see that every sodium is next to 4 chlorines, and every chlorine is next to 4 sodiums. These compounds exist as a 1-to-1 ratio, but they are surrounded in a positive, negative lattice. The catch is, this isn't even a 2D structure in real life, it would be a 3D structure. If we looked at this in 3D, although every chlorine would be next to 4 sodium atoms in a 2D slice, it would also have one in front of it and behind it, for a total of 6 of the other ion in any direction. So every sodium is surrounded by 6 chlorine ions, and every chlorine is surrounded by 6 sodium ions. It maintains that 1-to-1 ratio that we identified in the formula unit. But this helps explain why ionic bonds are the strongest intramolecular attraction, because the lattice structure is a very stable, very strong attraction, a very stable way to exist as a molecule. Let's look at how an atom from each group will act as it forms an ion. The first thing I want to look at is how many valence electrons. So let's start with group 1. The number of valence electrons in group 1 would be 1. Since it only has one valence electron, it would be easiest for this to lose, so the electron would be lost, that electron in order to reveal an inner shell that's more stable. Since it only has one electron, that's the only one electron that needs to be lost, and when it does that, it would form a +1 charge. I also know that sodium is on the left of the periodic table, and so it is a metal. Onto calcium, which would be found in group 2, meaning it would have 2 valence electrons. Again, it would be easier to lose the 2 than to gain 6 more, so this will also form ions by losing electrons. The electron would be lost. And then the number of electrons for the second energy level would be 2. Or, sorry, not energy level, but second column would be 2, because we've got to lose those 2 valence electrons. When it does that, it'll form a +2 charge, and then again, it is on the left of the periodic table. It is a metal. We're going to skip the transition metals and go over to group 3 or 13, which would have 3 valence electrons. Still easier to lose 3 electrons than to gain 5 more. It will lose all 3, creating a +3 charge, and again on the left of the stair-step line, so it is a metal. Group 4 is interesting. Going down the carbon family, they would have 4 valence electrons, and carbon itself is a non-metal, being on the right of the stair-step line. However, it is not going to gain or lose electrons. It's not going to form ionic bonds typically. They will form those covalent network structures, those giant structures. So we would not say that they would be interested in gaining or losing electrons, and they would not typically form an ion, so no charge. On to phosphorus, which would be in the 5th or 15th column, therefore having 5 valence electrons. At this point, it would be easier actually to gain 3 more electrons than it would be to lose all 5. Since it has 5 and wants to get up to 8, we would need to gain 3 electrons, giving it a -3 charge. And now we are definitely on the right side of the stair-step line. We're looking at non-metals. On to oxygen's family in group 6 or 16 with 6 valence electrons. If we're going to get to 8, we're going to need to gain 2 more, which would give it a -2 charge, and we are still on the right side, so again a non-metal. And last but not least, let's look at the halogens. So maybe bromine, group 7 or 17 would have 7 valence electrons, so it only needs to gain 1 more in order to form that ionic bond, in order to complete the octet. Gaining 1 electron would give it a -1 charge, and our halogens are of course non-metals. Notice we did not talk about the noble gases at all. Those are going to be completely inert and not forming any kind of ionic bond. Now that we talked about how individual atoms form ions, let's also look at polyatomic ions. So poly basically means many. So this is many atoms in an ion. So this is going to be formed when multiple atoms get together, but they don't neutralize their charges. So there will be a charge, hence it being considered an ion. However, that charge is actually spread over the entire ion. So there's an important term for that, delocalized. It's exactly what it sounds like. It is not localized in one location. So for example, when you look at ammonia, it has a charge of +1. That does not mean that there is a single hydrogen that is positive or that the nitrogen is positive. It is none of those things. That positive charge is delocalized or spread out throughout the ion. In your honors chemistry class, you were given a set of ions to basically memorize, but we never talked about where those ions came from. So the polyatomic ions are actually the conjugate bases of common acids. So we call them acid radicals. In order to form an acid radical, we are going to lose hydrogen ions. So we're going to take our hydrogen or acid compound and we're going to remove the hydrogen and we're going to form these common ions. So let's go through some examples. Removing 1 hydrogen ion from water would form hydroxide. Only 1 H, and removing a positive charge would leave a negative charge. So that's our hydroxide. Removing the H plus from nitric acid would form nitrate, NO3 minus. Sulfuric acid is interesting. If you remove both of the H pluses, you're left with sulfate, SO4 2 minus, because we would have removed 2 positives with removing 2 H pluses. It's also possible just to remove 1 of the hydrogens, which would leave HSO4, but since I only removed 1 H, it would only be 1 minus. And this can be named hydrogen sulfate, but more commonly it's called bisulfate. The prefix bi on a polyatomic ion actually indicates adding an H+. So to go from sulfate to bisulfate, the 2 minus becomes 1 minus because we've added a plus, and then we add the H in the front. We can do the same thing with carbonic acid since it's also diprotic or having 2 hydrogens. So we could remove both of them to form our carbonate, which would be CO3 2 minus since we're removing 2 H pluses. Or if you just remove 1 H, you would still have 1 left with the CO3, and then it would only be 1 minus since you only removed 1 of the H plus, and that would be bicarbonate. And our last acid is acetic acid, and you may recognize the acetate ion in here, C2H3O2, spelled out long ways since it's an organic compound to show how it's a carboxylic acid. The H that would be lost would be the one that's on the carboxylic acid functional group, and so that would leave behind our C2H3O2 minus, the version that you knew from Things to Know and Love, or you could keep it written out long ways as CH3COO minus for your organic chapters. So here we basically have our conjugate bases or acid radicals, our common polyatomic ions that came from acids. Now that we've discussed all the different types of ions we could form, I finally want to put them together into ionic compounds. I want to create the formula units of these compounds. So let's go through a couple examples, starting with this copper 2 sulfate. So you may remember that the 2, the Roman numeral after a transition metal, would indicate its charge, since transition metals can have multiple oxidation states. So copper 2 would be Cu plus 2, and it's going to bond with our sulfate, which we now know is SO4 2 minus. We just want the charges to cancel, which they do already. A plus 2 cancels with the minus 2. So the formula unit, or the ratio in which these ions would exist with each other, is a 1-to-1 ratio, CuSO4. Now let's look at sodium oxide. Sodium is in the first row of the periodic table, so it would have a plus 1 charge. Oxygen, on the other hand, is in the 6th row of the periodic table, meaning it needs 2 more electrons, and so it would have a minus 2 charge. That does not cancel out evenly. So we would need 2 of the sodiums in order to cancel with the oxygen. There's also the crisscross trick. So we could write this as Na2O1, which we wouldn't write. So it's Na2O for sodium oxide. And last, magnesium phosphate. So magnesium is in the 2nd group of the periodic table with a plus 2 charge, and phosphate, PO4, always has a minus 3 charge. So again, they don't cancel. So we're going to use our crisscross trick to figure out our subscripts. The magnesium needs a subscript of 3, and the phosphate I'm going to protect in parentheses to put the 2 on the outside. The 4 is part of the phosphate. The 2 indicates I have 2 phosphates. So it's Mg3, PO4 in parentheses, 2 outside the parentheses. Notice that in the end, the final molecules do not have charges. It can't be a compound if it's still charged. If it still has a charge, it's a polyatomic ion. The compounds are neutral. Let's move on to covalent bonding, where we are sharing electrons in order to achieve the noble gas configuration. There are 3 main types of bonds. Single bonds would only have 2 electrons, whereas we could have a double bond, meaning we have 4 electrons, or a triple bond for 6 electrons. Those 2 are split off from single bonds just in terms of organic chemistry usually. Single bonds will produce saturated compounds, whereas any double or triple bond would make the compound unsaturated. We still have 3 types of bonds. There is one other subcategory, a special type of covalent bonds. We call them coordinate covalent bonds or dative covalent bonds. This is going to happen when you have 2 different atoms that bring in a different number of electrons, and one of the pairs that is shared comes from the same atom. So carbon monoxide is a great example. Typically, when you form a bond, when you draw a Lewis structure, you're not really worried about how many electrons each species brought in. You can tell, since carbon's in the 4th row, it would have 4 valence electrons, and since oxygen's in the 6th, or column, not row, sorry, that would have 6 valence electrons. So we have a total of 10 electrons to work with. That's our budget for drawing the Lewis structure for carbon monoxide. And so if every line counts as 2, we have 6 bonds in our triple bond, plus the 2 lone pairs for a total of 10 electrons. And we didn't care that oxygen brought in more electrons than carbon. It does, however, indicate a coordinate bond. So I know this part might be new. We need to be able to identify coordinate bonds. So I'm going to draw this out piece by piece. First, I know that the Lewis structure would have a triple bond. That is a starting point. When I draw the covalent bonds, carbon would bring in 4 electrons. I know it would keep its 2 lone pairs, and then it would be able to contribute 2 electrons to the single bonds between the carbon and the oxygen. Then oxygen would come in, and it would bring with it 6 electrons. So it, of course, would have its 2 for the lone pair. Now it has 4 more that it can contribute to the bonds. So it will contribute 1 each to the single bond that carbon has already started. It still has 2 more, and both of those electrons will go into the bond that creates the third or triple bond. Having this pair of electrons that's in the bond between carbon and oxygen, but organically funded, only funded from the oxygen, that's the dative bond or coordinate bond. We would draw that bond in the Lewis structure with this arrow, showing that the electrons are being funded from the oxygen going towards the carbon. Around the world, there are lots of different ways to show Lewis structures, and according to IB, these are all relevant ways. They're things you might see in the textbook. I do want to warn you, these guys will get you in trouble in college in the United States, so just be careful. Dots are typically lone pairs and dashes are bonds. It's the way we know it. But I do want you to be familiar with some of these other ways you might see it in the book. One way that I do want to point out is down here with the X's and the dots is actually how I typically identify the dative bond, like the example we did with the carbon monoxide. Using X's for one atom and dots for another atom can help you keep track of which atoms provided which electrons. But in the end, you would still want to draw it with the bond that's equally provided for, like one from each atom as just a regular line. And if you happen to have a bond that is provided for by both atoms, then you would use the arrow. Or I'm sorry, both electrons provided from one atom, then you would use the arrow to show that dative bond. You still want to redraw your structure. So let's go over some important steps about drawing those structures. To start with, you want to figure out how many valence electrons that you have overall. This is going to be the budget for how many dots and dashes you can have in total. At first, don't worry about keeping track of which electrons came from which atom. That's something that you will need to do if the question asks you about a dative bond, but you would need to have a valid Lewis structure before you can start trying to identify the electron sources. So to start off with, we just are worried about total valence electrons. In this example, carbon in the 4th family would have 4 valence electrons. Hydrogen in the 1st family would only have 1, but there are 4 of them. So for methane, we would have a total of 8 valence electrons. So we know the total number of electrons represented in the structure cannot be greater than 8 or less than 8. The next thing that I'm going to want to do is create a little sketch of the structure so that I know the minimum number of bonds in order to even connect the atoms in general. In order to start drawing the structure, the first thing you're going to want to identify is the atom with the smallest electronegativity, which will typically be the atom in the beginning of the covalent compound. So in this example, carbon. You'll typically see carbon in the center if it has carbon. But if there's not carbon, then you're going to want to go with the smallest electronegativity. There is one example with water, which is of course because hydrogen can only have one bond. It's not going to be the center of any atom. So oxygen would have to be the center for water. Another thing you should know about the skeletal structure is that there's typically a clumping effect. There's a central atom and then the atoms surround it like a pinwheel. It's not going to be a linear effect. They are going to surround a central atom. One notable exception would be with organic compounds. Your carbon chains will be a more linear structure. But typically speaking, most of your covalent compounds will be a clumped structure. The next thing you're going to do is attach the surrounding atoms to the central atom and figure out how to satisfy the duet rule or octet rule for the compounds. So hydrogen does not need lone pairs since it only needs 2 electrons, which it has in the shared pair. And then chlorine, here only having 2 electrons, would need 6 more. Once you figure out how to satisfy the octet rule, you do want to double check that you haven't exceeded the total number of valence electrons available. If you have, you're going to need to pull in some double or triple bonds. You can also use a shortcut known as needed available shared in order to calculate the number of bonds. You're going to want to try to get the octet rule satisfied with the exact number of electrons available. Now this part is new as well. It is possible to have an expanded octet, meaning more than 8 electrons. So there are some conditions. One condition being that it has to have an available d orbital. So this is elements in period 3 and beyond, since the d orbital starts at 3d. Whenever you do have the option to have an expanded octet, after you have satisfied the octet of the surrounding atoms. So for example, the fluorine here has 6 electrons as lone pairs plus the 2 bonded. The fluorine has 8 electrons. After you have satisfied the other atoms, then the extra electrons will go on the central atom. The surrounding atoms will not be the atoms to have the expanded octet. It must be the central atom. Only once the exterior atoms are satisfied, and only if they have available d orbitals. Let's take a look at what atoms are capable of having an expanded octet. Which atoms have available d orbitals? As we just discussed, the 3d orbital starts with element 21. That means that any element that has a third energy level, so anything in period 3, would have a 3d orbital. Even sodium and magnesium would have empty 3d orbitals because they have a third energy level. Those orbitals exist, they are just empty. So anything with the third period and below can have an expanded octet, which means groups 1 and 2 are the only ones who absolutely cannot. We can actually narrow this group down even more. We know hydrogen follows the duet rule, so it can't have an expanded octet. Lithium, beryllium, and boron are typically metals not involved in forming covalent bonds, and if they do, they actually form incomplete octets because they're fairly electron deficient. We also know helium and neon, as noble gases, will not form covalent bonds. So we've actually narrowed this down to 4 atoms that behave in special ways when we're doing covalent bonds. Carbon, nitrogen, oxygen, and fluorine are the angels of the noble gases. They will always obey the octet rule when you are forming your Lewis structures. Now let's talk about boron and beryllium, which a minute ago I said these elements are electron deficient. They don't have a lot of electrons in total, only being in the second energy level, and they only have 2 or 3 valence electrons. This means that these compounds can be satisfied with less electrons, so we call this an incomplete octet. I want to point out specifically BF3 because we drew it a lot in honors chemistry with a double bond. That was when we were blindly following the octet rule, not considering the idea of incomplete octets. In reality, boron does not need 8 electrons. It is satisfied with 6 electrons, so it is all single bonded to the fluorine for the correct Lewis structure for BF3. Something else you should know about these type of compounds is even as a neutral compound, they still remain very reactive because they're still kind of missing electrons and would be really happy to seek them out and form another type of bond with some other reactant to turn into a different compound. So whether it's elements that absolutely do not exceed the octet rule or violate it in any way, or the atoms that have less than 8 valence electrons, we do know that the second row elements never exceed the octet. They only have a second energy level, 2s and 2p orbitals. There is no such thing as 2d. Without a d orbital, you cannot have an expanded octet. It is only once you reach the third row that you have the 3d orbital that you can exceed the octet rule. Again, completely satisfy the atoms around the central atom, and then if you have lone pairs left, put them on the center atom. We're also going to look at compounds where you have more than 4 things attached. So here's an example of PCl5. So we have 5 chlorines attached to this phosphorus. Phosphorus can have an expanded octet. It is in the 3rd energy level. Our next notes, Chapter 4, Notes B, will be on shapes and polarity. You want to be familiar with drawing Lewis structures before we get there, so make sure you practice that using Worksheet 1.